This is Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to explore the interaction between a falling magnet and a tube of aluminum foil. We'll explore Faraday's law that relates a time-varying magnetic field to a curly electric field which provides an EMF that drives current. These are the preview of our results. Our introduction to fundamental principles. We have Newton's second and third law, and our magnetic field of a dipole on and off axis listed below. Ohm's law, which shows that current equals volts over resistance. We have the force on a wire loop listed here. Faraday and Lenz's law, which is a change in magnetic flux through a wire loop, induces an EMF across the entire wire loop in the opposite direction of the change in flux. So this shows that EMF is the negative change in flux. N is for the number of rings. Then we also have our magnetic flux of a dipole listed below. Our procedure, we have our system is the magnet and the surroundings are the tube and everything else. Our procedure is we determine the north side of the magnet, drop the magnet 5 times vertically through the tube, record the amount of time it takes for it to fall, and then we use a code model to simulate a bar magnet being dropped and compare the times. Our assumptions are that no other forces except gravity and the magnetic force from the induced current act on the magnet, air resistance is negligible, and the bar magnet acts as a magnetic dipole. Our observations and checkpoint question 1 answer is that the magnet falls much slower when dropped through the foil than on its own. Without the tinfoil, it's dropped in 0.22 seconds. Our calculations are listed here, our initial conditions are also listed here, and our checkpoint question 2 answer is we can't use a ferrous tube because it contains iron, which has magnetic properties that would interfere with the falling magnet. My code is in the comments if you want to follow along. First, we have to set up our initial conditions over here on the right. Then we have to create a function to calculate the magnetic field of the bar magnet, which is the same that we did in Lab 3. And then we have to calculate the flux through each ring due to the falling magnet. Video lecture 43 has the formula over here. And then we use Ohm's law and Faraday's law to figure out what the ring current is, which is the negative change in flux over resistance equals the current. And then steps 5 and 6, where we're finding the B field at the ring, and then we're finding the force on the ring due to the B field. And we use this formula here where the B sine of theta is the magnitude of the B field times the direction of our dipole moment crossed with the direction of the B field. Anyway, but that is our how we find that. And then to find the net force on the magnet, we have to add the force from the magnet plus the force of gravity, which is right here, and then we have to update the magnet's velocity and position, which is using Newton's second law. And then interpreting the simulation, so the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. So blue over here is counterclockwise and red is clockwise. This is because the change in magnetic flux increases in the negative y direction, and the induced current counters this change with a positive y magnetic force. We can use the right-hand rule to figure out these counterclockwise and clockwise rotations. And what happens to the dynamics of the system when you flip the magnet around? So nothing happens by observation, so it'll fall the same amount of time, but the blue and red forces will flip, so it'll just look a little bit different in our code, but the time will be the same. And then how does the total time of your real-world system compare to that of your computational system? So the computational system is slower by about 0.5 seconds than the real world, but if we added stuff like air resistance or more precise measurements, or perhaps a different dipole moment or any other human errors, could probably fix this discrepancy. And then what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So it says that the forces are equal and opposite at times around 0.1 to 1.7 seconds because there's no change in velocity, so there's no acceleration. But then in the other times, it says that the force of gravity is much greater than the force of the magnet because the magnet is accelerating downwards and because there's a change in velocity. Our potential errors are that we could have the wrong measurements. We could, since we're not accounting for air resistance, that could be a possible error. The magnet could possibly be hitting the sides and we're not accounting for that. And then there's timing errors. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So from Ohm's law, we can see that a smaller resistance would increase the induced current and its opposing magnetic field, which would then slow the magnet further. So it would take a longer time to get through the tube. What if holes or slots were cut in the tube? How would this affect the rings current in your model? So there'd be less complete rings to induce an opposing magnetic field, and so the magnet would fall a lot faster because there's not much of anything opposing the gravitational force going down. That's all. Thank you.